It appears as though quantum mechanics and Fourier transform are a match made in particle heaven. The friendly Dirac delta function has a few more tricks up its sleeve. And in this problem, what we wish to do is find the Fourier transform of the Dirac delta and, using Plancherel's theorem, show that the Dirac delta can be expressed as 1 over 2 pi times the infinite integral of e to the positive ikx, or with respect to dk. There is an important note about this problem, though, mathematically speaking, and the author made a comment about it, stating that although the integral is clearly infinite at x equals 0, it doesn't converge to 0 or anything else when x does not equal 0, since the integrand oscillates forever. There are ways to patch it up. For instance, you can integrate from negative L to positive L and interpret this integral equation to mean the average value of the finite integral as L approaches infinity. The source of the problem is that the delta function doesn't meet the requirement, the L2 norm, of being square integrable for Plancherel's theorem. But in spite of this, this integration formula can be useful when handled with care. So clearly we will see this again in future context, but be aware this integral has some problems, and we kind of already knew that with the definition of the Dirac delta being what it is mathematically already from a previous example. Nonetheless, let's go ahead and find this Fourier transform. Well, to start, I guess we should write down the definition of the Fourier transform, which is what we see here. The goal is to find f of k, where f of x in red is equal to the Dirac delta, but note here that we have e to the negative ikx with respect to dx. We integrate out all the x variables here, and we're left with k only. So that should be your first cue. Now, if we plug the Dirac delta in, as we see here in the second line, note that we had this as a definition with the shifting property, and since this is shifted by an amount 0, we have to evaluate the green function, the exponential, at 0, which is what we see here. Awesome, cool, we like it. The exponential is at 0, go to 1, and so we see that the Fourier transform of the Dirac delta is equal to a nice constant. Easy enough, we like that. Now, if we want to use Plancherel's theorem, it is important to understand that this is the inverse Fourier transform, and so let's go ahead and state that as well. Here, if we want to recover the function f of x, we have to take the inverse Fourier transform, and that's why we have big F of k in here, and our exponential is positive ikx dk. Okay? So just be aware that this goes back and forth, and it's definitely used a lot, clearly, and it'll be used even more once we get to the formalisms of Chapter 3. But now that we know what we have here, let's go ahead and plug in the Fourier transform of the Dirac delta, which is equal to the blue 1 over the square root of 2 pi. No big deal. We've seen that before. And then here, we just got to simplify it. Now that we see that we have two factors of the same thing, we could just square it on the outside. But let's recall that our f of x that we plugged into the Fourier transform was a Dirac delta, so we can go ahead and write this down here. From f of x to delta x. Simplify out the constants, we see that we're left with an integral expression, again with the e to the positive ikx over dk. And you see squaring this gives us a 1 over 2 pi, the infinite integral of e to the positive ikx dk, which is exactly what we were trying to show. So all in all, not a bad question, pretty easy, pretty straightforward. Just make sure you carry your negative signs and your integration variables, and you'll be good to go. Well, thank you for watching. As always, until next time, happy learning.